Hello, class. In this video, I'm going to circle back to review certain problems where we solve quadratic equations using the square root property. Because in the last video, we briefly touched on this idea of imaginary numbers, and I think that we need to be prepared to sort of process certain radical expressions and know whether or not we're going to end up having a solution which is considered complex, a complex number, meaning it has a real and an imaginary part. Okay, so um, the objectives for this PowerPoint are just to get us through understanding the square root property so that we can move on to using our final method for solving quadratic equations, which is the quadratic formula. Okay, so up to this point, we should have been practicing solving quadratic equations by factoring and using the zero product property. We briefly saw how we can use the square root property to solve some equations, but again, we're going to do a little bit of a review here just so that we can set our minds at ease, have a few more examples to think about, okay? Before we move into our last method for solving quadratics, which is the quadratic formula. Okay, so in the previous video, we worked on this problem where we said if you have a quadratic equation where you have the ax squared term and the constant term c. Remember, the standard form for a quadratic equation is ax squared plus bx plus c equals 0. But if we encounter a quadratic equation where we only have the squared term and the constant, then we can solve those a lot more easily and very similar to the way that we solve linear equations by simply getting the x squared term by itself and then applying the square root property. So if you recall, what we would usually do for an equation like this is we would take a look at the constant, the minus 12. We would add it over to the other side of the equation so that we now have 3x squared is equal to 12. Okay. Then your goal is to get the x squared completely isolated. That is, we don't want that coefficient 3 in front of the x squared. We just want that coefficient to be a 1. Another way of putting that is that we want to cancel out the 3. Okay, so if we acknowledge that we could divide the 3 over to the other side of the equation, then we should end up with this equation, x squared is equal to 4, since 12 divided by 3 gives us the 4. Okay. And then we're in a really good position to apply the square root property. And all we have to do to apply that is take the square root of both sides of our equation. And we should then get x by itself is equal to either positive or negative 2. Sometimes we just say x equals plus or minus 2. Okay. But remember that for these quadratic equations, we should be getting two solutions. So we can also write this as a solution set where we have a negative 2 as one of our solutions and positive 2 as our second solution. Most quadratic equations that we work with in this class will have two solutions. There are some instances where we only have one solution, but we do need to be aware of how many solutions at most we should be ending up with, which is indicated by the degree or the highest exponent on that quadratic equation, which is a 2. So we should have two solutions at most, okay? So we looked at some of these practice problems in the previous video, okay? But then when we got to problem number D here, we saw x squared plus 1 equals 0, and that was a particularly interesting problem, even though it's very simple, okay? Now this introduces to a problem with taking square roots to solve quadratic equation. And this is something that hundreds of years ago mathematicians were confronted with when they were solving equations just like this one. When you approach this problem, what we usually do is subtract the 1, or whatever that constant happens to be. We cancel it out, move it over to the other side of the equation. And if that happens to be a positive constant at first, when we move it over to the other side of the equation, it becomes negative. So now we have this equation, x squared equals negative 1. Okay. And if we try to apply the square root property, that is, if we try to take the square root of both sides, well, on the left-hand side of the equation, we know that the square and the square root operations will cancel each other out. But if you recall what a square root is asking you, it's asking you, is there a number that I can square to get a negative 1? Okay? And you might guess, well, maybe negative 1 will work. But if we said negative 1 is our solution, then we should be able to square it and get a negative 1. But that's not true, because a negative times a negative, negative 1 times negative 1, would end up being a positive 1. Okay? And that is a correct statement. So really, it's kind of hard to see where the solution exists, since squaring a number will always turn it into a positive. Okay? Well, at least that's what we thought. Now, you might think that this might be an impossible problem, but mathematicians that really relied on there being a solution to the sorts of problems that they were working on in engineering, in number theory, and all kinds of branches of mathematics, they said, well, these square roots of negative numbers keep coming up, and we need to figure out how we can work with them so that we can get past these roadblocks. Okay? So they said, okay, well, let's pretend that we have this equation, x squared equals negative 1. And let's imagine that we just go through this the same way we would solve other quadratic equations using the square root property, where we take the square root of both sides of the equation. Okay. On the left-hand side of the equation, we should know that x squared, once we take the square root, that the square root cancels out the second power of the square operation, since they're opposites or inverses. So we should end up with x. So we have x equals plus or minus whatever the square root of negative 1 happens to be. And again, for now, we're just writing down the square root of negative 1, even though we don't know what this kind of simplifies to. Okay? So we could ask ourselves, logically, what number do we need to square to get a negative 1? And so you might go through the process that we just went through a little while ago. We might say that let's try positive 1. Well, that's not going to work because positive 1 times positive 1, it's going to be a positive. So we know that x cannot equal 1, since 1 squared is a positive 1, and we're trying to get a negative 1. We might then try negative 1, right? But again, x cannot be negative 1 either, since negative 1 squared is going to be a positive number. Okay? So we could leave it at this and just say, well, our answer is plus or minus the square root of negative 1. But when you have the square root of these negative numbers inside all of these complicated equations that those mathematicians were working with, they said that got really cumbersome. So let's just call this something else. And for a moment, we need to think about, where does this something else live on the number line? So where should this solution exist, right? Where do we put it on our real number line? Remember, the number line just starts with 0 in the middle. When we count to the right, we go to our positive numbers like 1, 2, 3, 4, and so on. To the left, we count our negative numbers, negative 1, negative 2, negative 3, and so on. And so what we know to be all of the real numbers contain all the positives, all the negatives. Those are what we call integers if they're whole numbers. All of the fractions, like 1/2 or 1 over 3, 7 over 4, those are all in between our integers. And then there's a bunch of other weird numbers like pi and the square root of 2 that are not perfectly like nice and pretty rational numbers that can't be written as a fraction. They have these really long extended decimal numbers that go on and don't have a repeating pattern, and the decimals never stop. Okay, so where are these other numbers that are the square roots of negatives? Well, it turns out that the number line as you know it is a little bit more complicated than it seems. That the imaginary numbers, as we call them now, exist on a number line that's perpendicular to the real number line. Okay, So the square root of negative numbers was such a wild idea that there was a certain sort of faction of mathematicians that hated that these things existed, and they ridiculed the mathematicians that would continue on working their problems using these square roots of negative numbers, like the square root of -1. Okay, so to ridicule them, they said these other mathematicians are playing around with numbers that don't exist. They're playing around with imaginary numbers. And even though that was just a derogatory term at first, that name has stuck and it has expanded how we think about the number system. No longer do we just have a single number line. We now have a number line that's perpendicular to the real number line, and we call this our imaginary number line. Okay? So similar to the real number line, we could count up in the imaginary direction or down in the imaginary direction. If we go up, we start counting with I, which is the first imaginary number, and then 2i, 3i, 4i, and so on. When we count down in the imaginary direction, then we're going to count -i, -2i, -3i, and so on. Okay, so there's a second number line where a bunch of other numbers exist. Okay. And for our purposes in this class, we really don't have to think about it any more deeply than that. But what is really cool is two things. You're going to see in Alex, they're going to start talking about complex numbers. And let me write this down. We have complex numbers. Now that we have two number lines, we call this number system the complex number system. Sometimes people call it the complex plane because a plane represents a two-dimensional sheet. Okay, so if we have two axes, then we're talking about a complex plane. And any point on this plane is a combination of a real number and an imaginary number. So for instance, if I put a point right, let's say right here, okay? Just like our Cartesian coordinate system, we could walk from the origin over to the real number 2. And so we would say this point right here in space has a real part of 2. And if we look at its imaginary part, it's in line with 3i. So we would say that this complex number is made up of 2 plus 3i. Okay. So now our number system has these points which may or may not have a real part and may or may not have an imaginary part, but if it has both, we call that a complex number. Okay. And in general, a complex number is written as a plus bi, where a represents the real part from the real number line, and the b represents the imaginary part that we can just count off from the imaginary number line. Okay. So again, I think that's really cool thinking that hidden in plain sight, the number line is actually more complicated, and we have this hidden dimension, and that's actually where all the imaginary numbers live. Okay. Like I said, engineers and mathematicians can do really cool things with this complex number system. In fact, this forms the basis for most modern technology, whether it has to do with signal processing in your cell phone, like making calls, getting GPS location, even figuring out what song you're listening to using apps like Shazam. Okay, all of that uses the mechanics of imaginary numbers and complex numbers. Okay. But for our purposes, when we solve certain quadratic equations, we're going to end up getting some solutions that sometimes are not real numbers, but are complex numbers. So if we look at this following example, we should see how we're going to approach solving these equations. So x squared plus 9 equals 0. All we have here is the x squared and the constant, right? And we should know that we want to move the constant over to the right side of the equation and isolate the x squared term, because then we'll be prepared to sort of use the square root property or take the square root of both sides of the equation, and then we can go on from there. Okay. So the way that this would progress is, I'm going to go ahead and write this on the screen so you guys can see it worked out. Subtract the 9, subtract the 9, so that we get x squared equals -9. Okay? Shouldn't be too hard to do that. But then you have to recognize that we need to take the square root of both sides of the equation just so that we can cancel out the second power. So now the second power gets canceled out by the square root. We're left with x is equal to, and we definitely don't want to forget the plus or minus symbol. Remember, our quadratic equations most of the time will have two solutions, so we have to remember that plus or minus symbol. Okay, but what is the square root of -9? Okay, well, there we might go and do some scratch work for ourselves and say, well, I know what the square root of 9 is, but that's not what we're dealing with here. We're taking the square root of -9. So we can't just ignore that negative sign. But what we might do is break this up into pieces because if I have a negative number, let's say we have the negative number -a, that can be rewritten as the positive part of the number a times -1, right? So in that sense, every negative number can be broken up into the positive part times a factor of -1. Okay. So similarly, if we're just looking at -9, we can call that 9 times a factor of -1, since that's the same thing as -9, right? And we'll make that replacement inside the square root symbol. Okay. Well, if you recall from our last video, we have some properties of radicals where we can break up the radical such that we now have the square root of 9 times the square root of -1. And you should be able to simplify the square root of 9 because that happens to be a perfect square. Now, you won't always get a perfect square, but in this case, it's a very nice and neat example. The square root of 9 is just 3. And as far as the square root of -1 is concerned, we are just going to call the square root of -1 I. Okay? So remember, whenever you see this I, that's encoding or containing all of the information about that -1 that we didn't really want to deal with here. Okay? But you need to remember the square root of -1 is equal to I. Okay? So wherever we have that square root of -1, we're just going to plug an I into our solution, and there we go. Okay? So going back to the equation we're trying to solve, the square root of -9 is simply plus or minus in this case, because we applied the square root property, 3i, and that's it. Those are our two solutions. Okay? So at this point, you might be losing sort of the forest for the trees a little bit. Remember that we're solving these quadratic equations. There's some facts that we have to recall, like most quadratic equations are going to have two solutions, and we want to write our solutions as a solution set. If we end up taking square roots of something that are a little bit more complicated, like something that's not a perfect square or something that's a negative number, then we have to take care of breaking that number down slowly so that we can ask ourselves, well, can I cancel out as many squares as I can in the case of non-perfect squares? And then in the case of negative radicands or negative numbers inside the square root, am I going to get an imaginary unit as part of my answer? Okay, and in this case we did. So our solution set is really -3i and +3i. Okay. Okay. So if you need to back up and review that equation, please feel free to do so. But as you go through the notes, you should see that I am kind of skipping over some steps here, but the essential pieces are in place. We moved the constant over to the right-hand side. It happened to be a negative. So we should be watching out for taking the square root of a negative once we apply the square root property. we get something like this. But because we want to simplify or express the square root of negative numbers using our imaginary unit I, then we need to think about breaking off that factor of -1 from that negative radicand, and then separating it out and sort of like boxing it in to the square root of -1 by itself, so that we can then call that I in a nice, neat package. Okay? Because if we were to leave it as 3 times the square root of -1, okay, let me write that down. If I were to write this answer as 3 times the square root of -1, well, writing the square root of -1 over and over in these equations that we're going to be solving, that's going to be really cumbersome. And so that's why we're saying this whole thing is going to be packaged into what we're calling I. Okay? So um, our answer should be x is equal to plus or minus 3I. All right. So let me switch over to the document camera so we could do a couple of examples that should yield some solutions that are complex solutions. Okay. So first, let's look at this equation that says 5x squared minus 3 equals -8 and start solving it. Well, if we need to solve this with the square root property, then we definitely need to add the 3 over to the other side of the equation so that we cancel it out here. We'll get 5x squared is equal to, and then -8 plus 3 is going to be equal to -5. Okay. Then we want to get the x completely isolated, so we're going to divide by 5 on both sides, such that now we have x squared is equal to -1. And there's our friend that we should sort of be preparing ourselves emotionally, spiritually, mathematically for taking the square root of both sides. Remember, when we do this, we're applying the square root property. I'm just going to call that SRP for convenience. But now we should have x is equal to plus or minus, and then we are just calling the square root of -1 I. So our solution set here is -I and +I. Okay, and we're done. We found both of our solutions. Okay. All right, the next one. Here we have 3x squared minus 4 is equal to -4. And just like the last problem, we want to move this constant term over to the right-hand side. So what we'll do is cancel it out by using the opposite operation. I have no idea why I just wrote a 5. We are adding 4 to both sides of the equation. There we go. Okay. So the -4 and the +4 will cancel each other out. We now have 3x squared is equal to, and then -6 plus 4 should give us -2. Okay. At that point, we do want to get our x squared term isolated. So we're going to divide by 3 on both sides of our equation so that we can cancel out that coefficient, leaving us with just x squared is equal to -2 over 3. And then finally, once we get it at this point, we can go ahead and apply the square root property, taking the square root of both sides, so that we have now x is equal to plus or minus whatever the square root of -2/3 is. Okay. Well, if we, go over to the right side of the page and do some scratch work, we might say to ourselves, well, this radicand, -2/3, could just be written as 2/3 times -1. Okay. And then since we're taking the square root of that thing, we can take the square root of both of these separately, right? We know, or hopefully we're getting familiar with, whenever we have the square root of -1, we can just call that I. However, the square root of 2/3, there are different ways to express this quantity, the square root of 2/3. But none of them is going to be like particularly satisfying here. We could split up the radical and call this the square root of 2 over the square root of 3. But these are both prime numbers. So if we were to try to simplify those radicals separately, they're not going to be, um, we're not going to be able to simplify them in any way that's going to be like really conducive to calling this simplified. So for this particular problem, I think I would be perfectly okay accepting your answers as the square root of 2/3 and then just putting the I next to it. That would be fine with me. Okay, so having two roots here doesn't seem particularly simplified here. Now, if you were to put this into ChatGPT or some other kind of math solving app, they would end up giving you an answer that looked nothing like this. I'm going to go ahead and say that this is safe for our class. But if you were to check this online, you might get a solution that looks more like the square root of 6 over 3i. And there's a whole topic working with radicals that is not covered in this class called rationalizing the denominator. Rationalizing the denominator. That is not a topic that we cover in this class. And so I don't expect you to be able to rationalize this denominator and give me an answer that looks like this. So if you get the square root of some number, whether it's a fraction or whether it's a whole number, that we can't break it down any further because the numbers inside, whether it's the numerator or denominator, are prime, then we're just going to leave that alone. It's going to stay inside the root, okay? But we do want to pull out that factor of -1 and then call the square root of -1i so that we clearly indicate our solution is an imaginary number here, okay? So we can write our solution set using the plus or minus symbol here. That includes both the positive square root of 2/3 I and the negative square root of 2/3 I. Or we could write it out long ways the way we did with the previous example. But I think that you guys should be able to figure that out well enough. Okay. All right. So I think we've talked enough about solving quadratic equations using the square root property, and hopefully we've sort of tackled the topic of imaginary numbers adequately enough so that you guys can get in there, mess around, and sort of figure things out, okay? But the final method for solving quadratic equations is going to be a formula, right? So there's not going to be a whole lot of thinking here until it comes time to simplify the formula. Um, all quadratic equations, whether they're factorable, whether you only have the squared term and the constant, all quadratic equations can be solved using this formula, okay? So the quadratic formula uh, is just a formula that we can sort of take the coefficients from the quadratic equation, plug them into the formula, and then it will give you your solution set so long as you can simplify it, okay? And it starts off with x is equal to, or whatever the variable happens to be. In this case, our favorite variable is x. X equals -b plus or minus the square root of b squared minus 4ac. Okay, all of that is over 2a. Okay, so it's kind of this big honkin' fraction that we have to work with, and it looks kind of intimidating. But if we sort of work it and proceed with caution, we should be relatively safe. So let's take a look at how we need to approach this. Okay, as any formula, my recommendation is that if you're given an equation that requires you to solve using the quadratic formula, or if that's what the instructions say, what you should always do is set up the formula with empty parentheses and then maybe back up and recall which coefficients go in which empty parentheses, right? Remember, those parentheses are kind of like placeholders for us in the same way that variables are placeholders, okay? So we're dealing with this equation, x squared minus 3x minus 3 equals 0, okay? And then we want to go ahead and write down the quadratic formula, but leaving our parentheses open so that we can have a space so we can substitute in the coefficients a, b, and c. Okay, so let's look at this on pencil and paper now. We have our quadratic equation written down. We have x squared minus 3x minus 3. And I've sort of been preparing you from the previous videos to be able to identify what your coefficients are and label them a, b, and c. So a is the coefficient in front of x squared. So if there's a number here, you put the number down for a. If you don't have a number, then that's an understood 1, okay? Because we have 1x squared. B is equal to negative 3, and that negative sign is very important. And then C is equal to negative 3 also in this particular problem, okay? So you guys have been labeling these coefficients since we started factoring trinomials using the AC method. So it should be somewhat comforting to come back to this A, B, and C, okay? Then we can prepare our workspace, x equals negative b plus or minus the square root of b squared minus 4 times a times c. All of that is over 2 times a, okay? So I'm setting up my quadratic formula by putting a blank set of parentheses everywhere that I have a variable. So if you need to see that formula again, it's right here. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, kind of a big thing. It will be really helpful to memorize that, but if you don't memorize it, you can always put it on your note sheet when it comes to the test. Okay. So if we run through this formula, we know we have a b here and a b here. So I'm going to take the value of b, which is negative 3, and I'm going to put negative 3 right here and right here. Notice that there is a negative in the formula, and so sometimes it helps to say the opposite of b, right? So if we have a negative in the formula and b happens to be a negative, you need to keep both of those negative signs, okay? So we have b in place, then we have minus 4ac, and a goes right here, and a also goes down here in the formula, okay? So we're going to put a, which is 1, right there, and right there. Finally, we'll put c, which happens to be a negative 3, in that last position, and then we're good to go. Now, like I said, the quadratic formula seems like it's very easy because we can just plug and chug. It should be fairly simple, but I find that students tend to make mistakes, especially when they're rushing. So my recommendation is to solve it in the following steps. First, simplify the negative b part. So we want to do this first. And if we have a negative times a negative, or two negatives, then negative times a negative will be positive. So we should get x is equal to positive 3. Then we can write plus or minus the square root of something all over something else, okay? The next thing that you want to simplify, because it's probably the next easiest thing, is the denominator. So this is just going to be 2 times some number. In this case, it's 2 times 1, which is going to stay 2 for our quadratic equation, all right? Next, I'm going to put a little 2 here. Next, what we want to do is simplify the radicand. So this expression inside the radical is sometimes called online the discriminant. And we need to watch out for the discriminant and not apply the square root yet, only because we want to check to see, is the discriminant going to be a positive number or is it going to be a negative number? Because if it's positive, then we could take the square root of that positive value and it won't put up too much of a fight. We may have to simplify a non-perfect square in that case, but it's something we should be able to do or go back and review the simplifying radicals video. Now, if the discriminant happens to be negative, then we're taking the square root of a negative number. So we still need to know how to simplify a radical in that case, but we also need to understand that if we take the square root of a negative, then we're going to get an imaginary number as part of our solution. Okay. So what I recommend is that what we want to do is, as our third thing, simplify the discriminant only in your calculator. So I'm going to grab my calculator and I'm just going to type in exactly as I wrote down, parentheses -3 squared minus 4 times 1 times -3, and then see what number I get. Again, we're just checking to see if the discriminant is positive or negative, and it happens to be a positive 21. Okay, so it's a positive 21. You should be able to do a little check for yourself. If that's a positive number, am I going to get an imaginary number when I simplify the radical? In this case, no, because we're just taking the square root of a positive number. Okay. So if that's okay, the next thing that we want to do is go ahead and ask ourselves, can we simplify this radical? Okay. And it won't always be the case that you can simplify the radical. And you might want to check to see if that's a perfect square. So we might go to the calculator and we might say, what's the square root of 21? If we get a god-awful decimal number, then we know that's not a perfect square. So we might try to break that down using a prime factor tree. 21, if we think of factors that multiply to make 21, that's going to be 3 times 7. And both of those numbers are prime. Okay. Because I don't have any repeated factors, I'm not going to be able to simplify any squares or cancel them out the way we did in that previous video, because the square root only cancels things that are squared. Okay. Since I don't have 2 copies of 3 or 2 copies of 7, then I'm just going to leave that as 21 and say that we cannot simplify that radical any further. Okay. So if we can't simplify the radical any further, then we can just say that our solution is going to be 3 plus or minus the square root of 21 over 2. Okay. And there's nothing more that we can do here. Okay. So we can stop here. But one thing that you might want to check is, in some cases, we may be able to simplify a solution like this a little bit further. But there's some notes that we want to take care of. So one, if we have, let's say, a real number here, a real number plus or minus a radical expression. These guys are not like terms. So we cannot combine them. The 3 cannot be added or subtracted with this square root of 21. They're not like terms. Okay. Similarly, if you have a real number plus or minus an imaginary number, those are not like terms either. Okay. So we don't want to be combining our real and imaginary numbers, and we certainly don't want to be combining our real numbers with our radical expression. Okay. But if we get a real number plus or minus another real number, then those would be like terms. So we want to go ahead and combine like terms if we can. Okay. And this isn't a one-size-fits-all situation. You're going to have to assess this for yourself, whether or not you can stop or whether or not you can go ahead and sort of simplify some of these equations a little bit further. Okay. So what I want to do is kind of maybe throw another example at you just so that we can see an example of using these quadratic formula to solve an equation. Okay, so let's take a look. cat. Sure, let's go with this one. Let's go with 4x squared plus 32x plus 16 equals 0. Okay. And remember, right now we're not trying to practice factoring. That's not what we're doing. We're really just trying to use the quadratic formula. So we're going to go ahead and set up our formula with those blank parentheses. X is equal to, big fraction, negative b plus or minus the square root of b squared minus 4ac. All of that is over 2a. Then we can go ahead and set that up with our parentheses as our placeholders. So b plus or minus, so negative b plus or minus the square root of b squared minus 4 times a times c. Then all of that is over 2a. Okay. You have to remember what is a, what is b, what is c. So we might just go over here and label a, b, and c. Okay. And then we'll just put those numbers in place. 32 is here and here. That's where b goes. Then a goes here and here. So this is going to be a 4 and a 4. And then 16 goes right here. Okay. Then, as I said in the previous example, what we want to do is simplify this part first. And if we have a negative 32, then we'll just call that negative 32. Plus or minus the square root of something all over 2 times 4 is 8. Okay. Then we're going to come back to our radicand, and we want to simplify the discriminant, right? Simplify this. And I always suggest to simplify in the calculator so that you don't have to do anything by hand here and possibly make a little mistake. So we'll grab our calculator and then type in just the discriminant, not the square root symbol. So we have 32 squared minus 4 times 16 and see what we get. In that case, we get 768. 768 now goes inside that square root. Okay. Then we can actually take a look at this. Since our discriminant is positive, we know we're not going to get an imaginary number, but we might just go ahead and grab our calculator again and see, is this a perfect square? 768, let's take the square root, and it's not a perfect square. Great. So if it's not a perfect square, then we will set up our prime factor tree, 768. And let's see what two factors go into 768. So we might do 768 divided by 2. That's going to be 2 times 384. Then we might do 384 divided by 2. And that's going to be 2 times 192. We can see if that's divisible by 2, 192 divided by 2. 2 and 96. We'll divide by 2 again. 192 divided by 2. Sorry, 96 divided by 2. So that's 2 times 48. This is going to be 2 times 24. 2 times 12. 2 times 6. And then finally we get 2 times 3. Good Lord, we have a lot of factors of 2 there. It's a very large number. Okay. Now, the way that I showed you guys how to simplify in this case for a really large number is let's go ahead and put together as many squares as possible. And I'm just going to go through the process even though it's kind of long in this case since we have so many factors of 2. So we have 2 squared here. We have 2 squared here. We have another copy of 2's here. And another copy of 2's here. So that's 2 squared. We had one, two, three, four pairs of twos. Then we finally got to our final three down there. Okay. We're taking the square root of these. So anyone that has a square is going to sort of break out or cancel that square root. So these cancel, these cancel, these cancel, and these cancel. So all of my twos came out. So I have 2 times 2 times 2 times 2, and then the square root of 3 stays in. Well, this is just going to be 16 if you multiply those twos together, root 3. Okay. So kind of a lot of work there for that one since it's so big. But now we can go back to our problem and say this is negative 32 plus or minus. We're replacing the square root of 768 with now 16 root 3 all over 8. Okay. So we simplified that radical. And like I said, this would be the end of the story, but we have to check some things. We have to check to see if we have a real number here that's being added to another real number, or is it being added to a radical or an imaginary number? Okay. So right here, we have unlike terms since we have a negative 32, and then this is a radical expression, 16 root 3. But you might try to put that into your homework platform, right? And it may tell you that you're wrong and it's not fully simplified. Okay. So yet another thing that you have to look out for is that this numerator expression may have a common factor that can cancel out a common factor with the denominator. So in that instance, if I notice that I have a negative 32 plus or minus a 16 root 3, think about the negative 32 and the 16. What number is the greatest common factor? What's the largest number that divides out of both of those? Or another way of thinking about it is, can I divide out an 8 from each of these? Okay. So I know that, the greatest common factor between negative 32 and 16 is 16. Okay. But the most I'm going to be able to cancel out is going to be a factor of an 8 with that denominator. So in this instance, I'm not going to decide to factor out the GCF. I'm just going to factor out a factor of 8. So let's say that I had an 8 that I wanted to take out from the numerator. So we're factoring out something, and that something is an 8. Well, 8 times negative 4 would give you the 32, plus or minus. 8 times 2 root 3 would give you back the 16 root 3. And so since I factored out that factor of 8, I can now cancel that factor with the denominator. So now I don't have a fraction. I just have negative 4 plus or minus 2 root 3. And that is fully simplified. Okay. Okay. Kind of a long one in that case. Like I said before, there's no one size fits all for simplifying these quadratic equations using quadratic formulas. You're going to have to throw everything in your arsenal at these equations sometimes. Okay. We pray and we're grateful for the ones that are very easy to simplify, but we do need to sort of like use our critical thinking skills to ask ourselves, okay, what is the easiest way to simplify this? Am I dealing with like terms? Do I have a common factor? Can I cancel something out of the denominator? What can I do here? Okay, and if you've exhausted all of the tools in your arsenal, then I would say it was safe to assume that you've simplified it as much as you can. Okay, so Um, what I want you guys to do is, well, definitely review these videos if you need them and if they're helpful. But what you're going to need to do is really brush up on your homework on solving quadratic equations, because the next topic that we're going to get into is going to take us back to graphing. We're going to start graphing quadratic functions and seeing what these things look like in a 2D space, right? We're going back to the Cartesian coordinate system. We're going to look at some graphs. We're going to analyze them. And when we have to do things like finding the y-intercept or mostly finding the x-intercepts for quadratic functions, we're gonna have to be able to solve quadratic equations. So now we're gonna put this together with a big picture, bringing back the graphs, bringing back the functions, bringing back the equation solving, so that we can put this sort of orchestra together. Okay. So make sure you're getting some rest, taking breaks, but definitely hitting your homework hard. Review these videos, speed them up, skip around, do what you got to do. Maybe watch them once, twice, three times if you need to, and definitely go get some help with your math homework in the tutoring lab. And I see you guys in the next video.